Hello everyone, my name is Mariel Gallardo. I am a master's student at the University of Florida and I work with Dr. Chinska Kehara at the Horticultural Crop Physiology Lab. And today I'm gonna show you the presentation I prepared for the last ASHS meeting. The title was Tailored Trellis System for Hop Production in a Humid Subtropical Climate. Hops, Humulus lupulus, are short-day perennial herbaceous plants, and with enough support they can reach up to 25 meters. The part that is commercially important for beer production is the female efflorescence, because hops add flavor, bitterness, and aroma to beer. The hop production and demand in the USA has increased in the last 10 years, from 24,000 tons in 2012 to 40,000 tons in 2021. The number of breweries is almost 8 times as it was in 2012. Now, there are 9,247 breweries in the nation. The price for wholesale of a kilogram of hops has also increased from $7.19 to $12.58. The increase of demand for locally grown ingredients has motivated the production of hops outside the traditional areas. But what is happening when we move a temperate plant to the subtropical climate? The plants are exposed to a different day length, and hops require at least 15 hours of day length during the vegetative stage. This is fulfilled in the Pacific Northwest, but when we have hop plants in central Florida at 27 degrees north, the maximum day length is only 13.8 hours, so this is an important abiotic factor impacting hop production. In 2016, when the first hops were transplanted in Northwest Florida, they experienced changes in their phenology. One was the incomplete vine elongation, they have premature flowering, and they also have a continuous cone development. All these changes didn't allow a one-time harvest, and all harvest was done manually, as you can observe in the picture. Since 2018, supplemental lighting was added in the field. With this change, all plants reached to the top of the trellis that was 5.5 meters. All of them have homogeneous flowering, and it was possible to have one-time harvest, as you can see in the photo. Supplemental lighting enables a double season hop production, spring season from February to mid-June, and fall season from mid-June to mid-November, then senescence followed by dormancy, and the cycle repeats. With supplemental lighting, the short day length limitation was solved. However, there are other management practices that need to be tested and tailored for subtropical conditions. One of those is the trellis system selection, because this is an important investment a grower needs to do when starting a hop yard. For that reason, we have the objective to evaluate the effect of trellis design and trellis height on growth, yield, and cone quality of cascades. Our final goal is to develop an optimum trellis system for double season production in a subtropical and humid climate. For that, we transplanted cascade tissue culture plants in the Gulf Coast Research and Education Center located in West Central Florida, in the south of Tampa. The experimental design was an RCVD with 4 replicates and 10 hills or plants per plot. They have a split plot arrangement, where the main plot was the trellis height with 3.7, 4.6, and 5.5 meters as treatments, and the subplot was the trellis design with a straight and V trellis. On the photos on the left hand, you can see the straight trellis, and on the right hand, the V trellis. The main difference is the number of twines they have. The straight trellis will have only 2 twines, that are held by one central wire in the top of the trellis system, and the trellis will have 4 twines per plant held by 2 parallel cables connecting the 2 poles in the top of the trellis system. The data collection was done during vine growth for stem diameter, internal length, and vine number, and during harvest for yield and con quality. We use SAS with Glimex procedure for data analysis, and for linear regression analysis we use sigma plot. Results. In the vine growth variables that we measure, we didn't find any significant linear regression with yield. However, when we evaluate the dry weight of stems, we observe a positive and significant linear regression between stem, dry weight, and yield. The reason why the dry weight of stems was correlated to yield could respond to the fact that flowers are developed in the lateral, which is a stem material. It means a higher number of lateral and longer laterals allows more space for flower induction, gum development, thus yield. And that can be a reason why these two variables are related. In yield, there was no interaction between trellis height, season, and trellis design, but there was a significant interaction between trellis height and season. In the first season, the higher the trellis, the higher the yield, and the difference between the 3.7 trellis and 5.5 meter trellis was 78%. A similar trend was observed in the year 2 fall, with a difference of 215% between the 3.7 meter trellis and the 5.5 meter trellis. The other two seasons didn't show a difference between heights. Another important thing that I would like you to notice here is that this perennial crop didn't behave as we expected. It's usual that the first yield will be low in a perennial crop, and then it will increase in the second and third harvest, and then will get stable for many years until they start to decline. In this case, the highest yield occurred in the first season. We believe that this can be related to the lack of dormancy period between spring and fall. As I mentioned before, there is no a time between the harvest and the initiation of the fall season. So these plants don't have time to translocate nutrients to the roots to start a new cycle. When we pull the data for trellis design, we observe that big trellis had always 24% higher yield than straight trellis. This can be related to a better exposure to light or a less competition for light between the twines. In both trellis designs, we kept the same amount of vines. However, the distribution is different because straight trellis had only 2 twines and big trellis had 4. This is a visual example of the plant architecture differences between all the treatments. On the top, you can see the straight trellis, and on the bottom, the big trellis. These photos were taken during cone development. The main difference that I would like you to see here is the biomass distribution. In a straight trellis, we observe that the biomass is allocated in the top of the trellis, and probably it's not clear here, but if you see some green balls or dots, those are the cones, and they are allocated only in the top of the trellis. and that is clear in the 3.7 meter trellis. However, in the V trellis, there is a more homogeneous distribution of the biomass and the cone formation. This is what can be affecting the yield, because this biomass is not only related to leaves, it's also related to the number of laterals that are developing cones in all the trellis height. Something that can be affecting this biomass distribution that I saw in the previous slide can be the lateral shoot development. In this series of photos, you can observe the lateral aging. So the photos that have the bulb, the red bulb, are the ones that are taken during the supplemental lighting period. So you will observe that the laterals are green and they are growing 7 days after they keep in the same situation. They are not extending, and 17 days after the first picture they start to develop a browning tip, and they are still in vegetative stage because we are keeping the supplemental lighting and they continue browning. When we induce flowering by suppressing the supplemental light program, there is no response of these laterals. They just continue aging and they don't develop any flower or cone. And this was observed mainly in the lower part of the trellis. And this is a factor that can be affecting all the plant architecture and yield. So there is an additional point to study to see what management practices or treatments can improve the lateral age or delay the lateral aging. In cone quality, here I'm showing the data for alpha acids and essential oil. Both of them were affected by season, and they were not affected by any interaction. Alpha acids reached the commercial average in year 1 spring and year 1 fall, and overpassed the commercial average in year 2 spring. However, it dropped for year 2 fall. This is a unique behavior because in long-term studies of other cultivars and also cascade, the common behavior is to have the highest alpha acid content in year 1 and then dropping to the second season, third season until it is stable. There are some changes due to environmental conditions, but they usually don't get up to the first season alpha acid content. So this brings or opens opportunities to see what could be the management practices or environmental conditions that allow this increase in alpha acid content regardless of the plant age. Alpha acid was also higher in big trellis than straight trellis. This is a good sign because big trellis was also the trellis with higher yield. So it will reinforce the idea of selecting big trellis as the best trellis design. It's also important that there was no significant effect of trellis height, because this will allow us of selecting the trellis with highest yield for the optimum trellis system without affecting the cone quality. In essential oil, the numbers are low, but again it was able to go up to 0.674 milliliters per 100 grams in year 2 spring, so that there is possibilities for increasing this essential oil content. Finally, the summary or take-home message. Yield reduction from spring to fall season can be related to lack of dormancy stage before fall season. The increase in trellis height and stem dry matter positively affected yield, but not reducing cone quality. Trellis height above 4.6 meters allow more internode and lateral formation, thus space for cluster of cones. The axillary meristem aging at flower induction could be an important factor affecting yield. And finally, bee trellis may reduce shade syndrome and allow more lateral and flower formation, improving yield. Finally, I would like to thank all our sponsors and collaborators in this project. All this work was done with the support of the Horticultural Crop Physiology Lab and all of the former members and present members, and also the funding of the Specialty Crop Block Grant.